Hello and welcome to the video on antiderivatives and indefinite integrals. Now that we've completed the first portion of the class where we dealt with the derivatives and application of the derivatives, now we're going to go in the other direction, thus the antiderivative. So our objectives for this video are: number one, we want to write the general solution to a differential equation. Number two, use indefinite integral notation for antiderivatives. Number three, use basic integration rules for antiderivatives. And number four, find a particular solution for a differential equation. Now let's start out here with looking at the definition of an antiderivative. A function capital F is an antiderivative of little f on an interval I when f capital F prime of x equals little f of x for all x in I. Let's say that again. A function capital F is an antiderivative of little f on an interval I when capital F prime of x equals little f of x for all x in I. Let's take a look at an example of what this means. Let's start out here. We're going to take a look at this first one, capital F1 of x equals x to the fourth minus 2. It is an antiderivative of 4x cubed because if you take the derivative of this, you're going to get the 4x cubed. By the power rule, the derivative of x to the fourth is 4x to the third. The derivative of the 2 is 0. What I also want you to recognize here, though, is that antiderivatives up here, when we talk about it, up here, we always talked about it as an and, not the. It's because the antiderivative is not unique. F2 is another function that when I take its derivative is going to give me 4x cubed. So capital F1 and capital F2 would both be antiderivatives of 4x to the third. Please note also that we can find there are going to be an infinite number of functions that are going to be antiderivatives of 4x to the third. It's all going to depend. Use a different constant, add a different constant to x to the fourth. I'm going to get a different function whose derivative would still be 4x cubed. The question then is, how do we represent an antiderivative? Well, what we're going to have here is if capital F is an antiderivative of little f of x on our interval I, then g of x, capital G of x, is also going to be an antiderivative of f of x if and only if g of x, capital G of x, equals capital F of x plus some c, where c is a constant. This c is called the constant of integration. And we would sit there and say, that g of x, capital G of x, equal to capital F of x plus c is a general antiderivative of little f of x. So really what's going to happen, you're going to have a function, little f of x, you're going to find its antiderivative and then put a plus c at the end, and that will be the general antiderivative. Let's take a look at an example here. In this case, we're going to let f of x equal, little f of x equal 3x squared. Well, what I want to do to find my antiderivative, my general antiderivative of this, I need to identify a function whose derivative is going to be 3x squared. Well, thinking about that and thinking about the power rule in terms of finding a derivative, it doesn't take long for me to come up with the idea that the antiderivative, an antiderivative of 3x squared, is going to be x cubed. So in this case, I would say that capital F of x is going to be x to the third plus c, our constant of integration. Whenever we're finding an antiderivative, we need to go through and include that plus c at the end. Now the question does come into play then is, how do we know we're supposed to take an antiderivative? Well, the other thing you have to keep in mind here is that to do this, we're going to have a symbol, and that is called the integration symbol. And so that integration symbol is right here, and that symbol it's like an elongated S, if you will, but that tells me I need to go and find the antiderivative. And so when I see that the integral of f of x dx. Now that integral sign and the dx, those you got to think of that as that's part of an operation. And once you find the antiderivative, you don't need those again. So that integral, the integral of f of x dx is going to be capital F of x plus c. For example, let's let f of x, little f of x equal 2x. Then if I take the integral of f of x dx, that's going to be the integral of 2x dx. And I know that when I take the antiderivative of 2x, I'm going to get x squared. So the answer on this is going to be x squared plus c. Another thing to keep in mind here, I'm referring to these a lot of times as antiderivatives, and I've also used this integration, and I've said integral a couple times. The answer, an antiderivative, is also known as an indefinite integral. And so you'll hear both those terms used, and you must remember that they are interchangeable. An antiderivative is equal to an indefinite integral. Now, another thing you're going to see in this section is what's called a differential equation. And what that means, a differential equation, is an equation that involves derivatives. So in our case here, we have a little bit more formal definition. A differential equation in x and y is an equation that involves x, y, and the derivative of y. That derivative can be written as y prime or dy dx. I will usually write it as dy dx, and you'll see why in a second when we talk about how we solve them. But you can use the y prime. So this y prime equals 4x squared minus 2 is a differential equation. Same thing with dy dx equals the cosine of 7x, or dy dx equals x plus 5. Or the fourth one here, dy dx equals x times y squared. Now, for our purposes right now, the ones that we're going to be dealing with are going to be these first three. This fourth one will be something we'll work with at a later time. Now, when I go through and find this general antiderivative, it is also known as the general solution to the differential equation. So when we hear general solution, just really saying find that general antiderivative or the indefinite integral of our function. Now, to go about solving a differential equation, what I'm going to do is I'm going to let dy dx equal some f of x, some little f of x. So I'm going to write that in the differential form. So if you remember when we dealt with at the end of chapter 3, we talked about differentials. So and one of the things we had is that dy was equal to f prime of x dx. Well, in this case, I'm going to write it in that differential form. I get that by just multiplying both sides by dx. So I'll get dy equals f of x dx. And then I'm going to take the indefinite integral of both sides. So I'll have the integral of dy equals the integral of f of x dx. Well, I know the integral of dy is just going to be y itself. And the integral of f of x dx, we've talked about, that is going to be capital F of x. And then we do have to include that constant of integration. So I will get capital F of x plus c. Let's look at another example here. In this case, I have dy dx equals x squared plus 2x minus 1. So the first thing I want to do is I want to go and write that in its differential form. And to do that, I just multiply both sides of this equation here by dx. And when I do that, I'll get dy equals x squared plus 2x minus 1 dx. And then the next thing I'll do is I take the indefinite integral of both sides. So I have the integral of dy equals the integral of x squared plus 2x minus 1 dx. So when I do this problem here, I go through, the first thing I need to do is take the integral of dy. And I know the integral of dy is just going to be y equals. Now in this case, what I have to do is I need to identify what functions have a derivative of x squared, what have a derivative of 2x, and the derivative of minus 1. So what I'd like you to do, pause the video right now and identify the antiderivative of each term you see in this part of that indefinite integral. Pause the video. Once you have your antiderivatives, come back and we'll talk about what the results are. Welcome back. So in this case, when you take what we have to do is take the antiderivative of each term that we have in here. So the first thing I have to do is find the antiderivative of x squared. Well, what function has a derivative of x squared? Well, I know the original function had to involve an x cubed, so I'll put that there. But when I take the derivative of this, it's the 3 in that x cubed is going to multiply some number in front, so I'm going to get a 1/3 x cubed. 1/3 x cubed, if I take the derivative of that, will be x squared. Plus, the antiderivative of 2x is just x squared. And the antiderivative of -1 is going to be minus x. And so I'm going to have that, and then plus our c, that constant of integration. So our general solution to this differential equation, the differential equation dy dx equals x squared plus 2x minus 1, is going to be y equals 1/3 x to the third plus x squared minus x plus c. Now, at other times, what they're going to ask you to do is they're going to ask you to find a particular solution to a differential equation. In other words, what that means is that's just saying you're going to be given some information that will allow you to find out what the value is of that constant of integration. You'll be able to identify it. You'll be able to get a numerical value there. So, what we have here in this case is I have a differential equation. I'm going to look at dy dx equals 2 cosine of x. And my initial condition in this is going to be that capital F of pi over 6 is going to equal 4. So what I'm going to do with this is I write it in that differential form. So I'll have dy equals 2 cosine x dx. Take the indefinite integral of both sides. The integral of dy is y. And the integral of 2 cosine x dx, well, that's going to be 2 times a function whose derivative is cosine, and we know that's going to be sine, plus c. So right now what I have is I have a general solution to this differential equation, y equals 2 sine x plus c. Now this is where I'm going to use my initial condition, the condition that capital F of pi over 6 equals 4. In other words, when I put pi over 6 into my general solution, I know it's got to be 4. So when I do that, when I plug everything in, I will now have 4 equals 2 times the sine of pi over 6 plus c. And now I got to think back to my unit circle, and I remember, oh, sine of pi over 6, that's equal to 1/2. So I have 4 equals 2 times 1/2 plus c. When I simplify that, I get 4 equals 1 plus c. So therefore, I know that c is equal to 3. And so, taking this value for c, I plug it back into this spot, and I get my particular solution, which is y equals 2 times the sine of x plus 3. That would be the particular solution to this differential equation subject to this initial condition. Now you might be thinking right now that there's a lot that you have to work with on this because we've had so many derivative rules, and that's true. Every derivative rule that we've covered to this point has an associated integration rule. Okay, and you're going to need to recognize those. So a lot of times, sometimes it's helpful when you're looking at that at the indefinite integral or you identify what function is going to have that as a derivative. Other people like to have the rules, so if you can find all the integration rules formally stated basically right next to their associated derivative rule on page 246 of the textbook. If you go there, it's it's the bottom part of the page. Just lists off a bunch of the integration and derivative rules that we've covered. Well, the derivative rules that we've covered so far, and then the integration rules that go along with them. Finally, what we want to recognize here, and this is an important aspect for you to keep in mind, and I think you probably have this already, but I want to state it. It's that if I take the integral of at capital F prime of x dx, I'm going to get capital F of x plus c. In other words, integration is the inverse of taking a derivative. Taking an integral will undo what I did when I took the derivative. By the same token, if I take the derivative of the integral of f of x dx, that itself is going to be little f of x as well. And so what we get from that is that taking the derivative is the inverse of integration. It's important to keep those two in mind, that they have that relationship, and that's going to come to play a little bit later as well. This does now conclude my video on finding on antiderivatives and the indefinite integration. In class, we will spend some time doing some additional examples of finding an indefinite integral and doing the antiderivative. And we'll also talk a little bit more about some of the rules and applying them, especially taking a look at some of the rules involving the trig functions or the sum and difference formulas as well. So with that, and we'll also be talking about another feature that we'll deal with more as we progress through the year, which is called a slope field. A slope field is a tool that we use to help us find an approximate solution to a differential equation. So you'll see that as well. So next time in class, we will spend time looking at examples of indefinite integrals and also working with slope fields. So have a good day or evening, whatever it might be for you, and we'll see you in the next class.